Hello, last time everybody. In case you've forgotten my name, it's David. The reason I do this, if you've ever seen any of the other seminars that I've done recently, is because I get people in the Maths Learning Centre, actually I had one just the other day, saying, I watched the revision seminar and and it was all about this and there was all these things happening, and I'm sitting there going, yeah, that was me who was giving that revision seminar, and they didn't know. So I think if my face is on here, then there's a chance that you might recognise me rather than just my voice. All right. Okay, I've been asked to talk about partial fractions. It's high time I did. Partial fractions is a method of rewriting rational functions. In that sense, it's not really a technique of integration at all. It's actually a technique for rewriting rational functions in more helpful formats, which happens to make them easier to integrate. But it will also come up if you ever do Laplace transforms when you do differential equations, if you ever do differential equations 2 or engineering maths 2A, possibly 2B, or dynamics and control in second year, it will also come up there. So as a method for turning rational functions into things that are more helpful, it's a good method and is used in more than one place. In Maths 1A, we use it to do integrals. So when I say rational function, what I mean is something that is a polynomial on the top and another polynomial on the bottom. That's what I mean by a rational function. Okay. Note that a polynomial could just be a number. It could be 1 over polynomial, and that's still a rational function. So anything that's got polynomial or constant on the top, polynomial on the bottom, constant on the bottom doesn't really count because you know how to do that already, is what partial fractions is for. And what we're going to do is that we're going to take our rational function, we're going to split it up into different parts, hence the partial, different fractions that all add together to give the same answer. All right. Right. So there's this sort of general idea of things to do, and then there's specific cases that you can do a bit more quickly if you notice them. So it goes something like this. First you want to rewrite it in such a way that it's something, possibly nothing, something plus something that has a higher degree on the bottom than on the top. I'll read this shortly. You want it to be polynomial plus polynomial over higher degree polynomial than the one on the top. It doesn't matter how it relates to this one, that's irrelevant. It's how it's higher than the one on the top of the same fraction. That's what you need to do. You might not have to do that. It might already have a higher degree on the bottom than the top, and then you're good. But you might have to rewrite it like that. And the way that most people go about doing that is doing polynomial long division. And I'll talk about that shortly. The second step is to factorize the bottom of the new polynomial. Sorry, the new rational function. And the third step is to write what format you think the final partial fraction is going to be. And there are specific rules for what those formats are, and I'll talk about that in a second. And then what you're going to do is figure out what numbers go in that format to make it work. Okay, so figure out the numbers to fill out that format, and you normally do that using putting everything over a common denominator and equating coefficients. And then you're done. I should say that in some courses and in some places where it's more useful, instead of equating coefficients, you sub stuff in and it creates equations to solve instead. And I'll illustrate that at the time. Okay, that's the plan. That's how partial fractions works. And the theorem of partial fractions says that if you do that, it will work. Okay, that it is actually possible to split up a rational function into its appropriate partial fractions if you choose the format correctly. If you do not choose the format correctly, it might not be possible. That's the theorem. The theorem is all about this format. All right. Do you want me to do a polynomial division? No? Okay, I'll skip that bit. I probably have done it in the other seminar. Right, so polynomial division, I believe you can also look back at the Maths 1M to see how that's done as well. I've learned a new method for it recently, which I haven't tried yet, so I'm going to not tell you to do it in your exam, because that's not what they're expecting. So what we need to do is the format that we get, okay? And it works better with an example. Okay, so we're going to do step 3 onwards. I'm going to assume it's already factorised for us. Okay, so the first thing you need to know about the format that we're looking for is that if you see individual terms that are x plus something or x minus something or just an x, linear terms, then the format that you need is this. Constant over each linear term. And that's the format that we need, if they're all linear terms. Okay. I'm going to finish this one off and then I'm going to come back to the formats for the others. So linear terms by themselves, this is what we'd need to do. And when you complete this off, you're going to put this all over a common denominator. It doesn't matter if it's the lowest common denominator, though that would be the most helpful. What you want it to be is the same denominator as this. Some people, when they do this, what they do is they just multiply both sides by that and it produces the result they need. So if you just multiply everything by this on the top over here, it'll work. But I tend to look at it by what's missing. The x minus 5 here, and I'm missing an x plus 2 and an x. Here it's got an x plus 2, I'm missing an x minus 5 and an x. And with this one, I've got an x and I'm missing an x minus 5 and an x plus 2. In case this helps you, you can imagine this x as an x minus 0, which makes it look more like the others. Okay, sweet. And now, this fraction is supposed to be the same as this fraction, and if two fractions have the same denominator, which they do, then in order for them to be the same, it's the numerators that have to match. So I have a couple of choices in how to do this. I can sub in values of x. I could sub in x equals 5, for example, and that will tell me what a is. Technically, I can't really sub in x equals 5 because this rational function is not defined when x equals 5. So what I'm really doing is a limit, the limit as x goes to 5. But it all works out in the end. So I could do that if I wanted. Alternatively, I could expand it all out and equate the coefficients. It doesn't matter which you do unless MapleTA, for example, asks you to do a particular one of them, right? Which is what it did recently. So one approach is to sub in things until you get 3 equations and 3 unknowns, okay? So I could go when x is equal to 5, I have 3 times 5 squared plus 5 times 5 minus 7 is equal to a times 5 plus 2 times 5 plus b times 0 because 5 minus 5 is 0 plus c times 0 because 5 minus 5 is 0, and I magically get an equation that tells me what a is. So 5 squared is 25. I actually have 4 25s, which will be 100, so we get 93 here. 5 plus 2 would be 7, 7 to 5, 35. And so a is 35, 93 on 35. And then I could continue doing that same procedure. X is equal to 0, which would give you me minus 7 on this side. And on this side I'm going to have a times 0 plus b times 0 plus c times minus 5 times 2. And so I get minus 7 is minus 10 times c, and so c is 7 over 10. And finally, if x is equal to, what's the other number, minus 2, that'll clear out these ones here. That'll make that 0. So I'm going to get 3 times minus 2 squared plus 5 times minus 2 plus 7, minus 7 is equal to a times 0 plus b times minus 2 minus 5 times minus 2 plus c times 0, and so I get b, oh gosh, 3 times 4 would be 12, minus 10 would be minus 22, minus 7 would be minus 29, and this would be minus 7 times 4. And so b equals, ta-da! Okay. Is that what you got? Okay.
No, it's just a better method than the lovely way.
Yep. So one of the problems with this method is when you have squares up on the top and you end up wiping everything out. So you might just have to pick a random number that doesn't wipe something out at some point. So hopefully I'll show one of them. And that could be one approach. The other approach is to expand everything out. And so it would be like ax plus 2x plus bx minus 5x plus c, x minus 5, x plus 2, just like a squared minus. Thank you. Squared minus, let's see, we've got minus 5x and plus 2x would be minus 3x. And so we get the constant term is, there isn't one here, and there isn't one here, and we get minus 10c, and that has to match with the constant term over the other side, which is minus 7. The x term, we've got 2a, a times 2 here, we've got minus 5 times b here, and minus 3 times c here, which is supposed to come out to 5, and the x squared term, which is a plus b plus c, which is supposed to come out to 3. And now we have some simultaneous equations to solve to figure out what a, b, and c are, which you could do with matrices if you wanted. Nothing's stopping you doing that. But as you say, you know, solve, and then you end up with a equals b equals c equals. But as you say, that's longer a lot of the time. However, most of the time when they write a maths exam question, it will be such that they're not too hard to solve. So do what you think is best. And if you were doing this because you were, had a problem that had to do this, you would have access to a computer where you could sub it in and do the row operations and figure it out, and you wouldn't have to do any of the work yourself. In fact, if you really had to do this yourself, you'd probably go to MATLAB and ask it to do it for you, and it would do the whole thing all by itself. So, unless, of course, as I do, I love integrating. And it's fun to do things that you know how to do. Okay, so either way, what we end up with is being able to rewrite as a over x minus 5, and a was 93 over 35, plus b over x plus 2, and b was minus 24 over 14, 29 over 14, and c, which was 7 over 10, no, that's not a b, sorry, over x. And these things are conveniently easy to integrate compared to the thing that we started with, because it's the constant on the top is still going to be there, and the integral of 1 over x minus 5 is ln, absolute value, x minus 5. So the goal here is to turn it into something that I know how to integrate. So it's really just technique 1, but fancy. All right, so that's the general idea. Okay? Right. So I want to just tell you about the formats. It'll be easier. The formats are listed in your lecture notes. But I'll do a couple of examples afterwards. Okay? So we already know the format that if you see on the bottom, an x minus a and other stuff, then there will be in here somewhere an a on x minus a, something like that, plus other stuff. That's sort of what it's going to look like. If you see this, then you have a on x minus a squared, and another one just for the first power. You have to include one for every power of this all the way down to 1. If I saw this, I would have 1 for x cubed, 1 for x squared, and 1 for just x. Like that. And that goes for every linear term. So if you've got one that's cubed and the other one to the 4, the cubed one will get 3 pieces, the one with the 4 will have 4 pieces. If you just see an x to the 5, it'll have an a5 over x to the 5, a4 over x to the 4, a3 over x cubed, and so on. That's format number 1. We doing okay? Do I need to clarify something? Okay, cool. Yep.
That means the next part, let's say, if the part of the polynomial would be b on x take a squared plus b. Let's say with the second row we've done there, say it was like 3x squared plus 2x plus 3. You would then, after you've done the a2 on x take a squared plus a on x take a, you would have b on x take a squared plus b on x take a.
No. I will do an example later to show how to combine them. Okay, the next format, and you get to choose what to do with this. So I might do an example here so you can see how to combine these at this stage. So we had single terms and we know how to combine them together, and now we've got linear terms with powers. So as an example, I could go like, is this the sort of thing you were talking about? Though I don't really want to do 7 because that's going to take me forever. Something like that. So this would mean I'd have some pieces that go with this. The reason I've done 3, 2, 1 is because then it matches the powers that they go with. This one will have 2 pieces. Because it's there twice. And this last one will only have 1 piece because it's only there once. For consistency, I will call it x take. Like that. Is that what you were thinking of? Okay. Okay, so each part, depending on what power it is, produces several different parts. You must do this. So if you don't include these ones, it is just possible that you will be very lucky and it will work. Otherwise it won't work, and what will end up happening is that back at this stage when you do your equations, they won't have a solution. So that's what the theory of partial fractions does. You may be asking yourself, how would I integrate such a thing? Maybe. I'll deal with that in a minute. Okay. I'm doing it this order for a reason, because integrating it is a whole separate thing from creating it. Because maybe next year you don't want to integrate it and you want to do something else. Okay. So this is my first rule. In fact, I'm going to be so bold as to highlight this rule with a closed figure, which may or may not have been intended originally to be a rectangle. Okay. The next thing is what happens if it's not linear, but it's quadratic in such a way that it doesn't factorize. So it may be over x squared plus 1, for example. Something like that. So if it's like x squared plus 1, it's not going to factorize. You'd have to use complex numbers to do that. Now, the secret is you could use complex numbers to do if you wanted, but you'd have to do some integration involving complex numbers, and there'll be more minuses, and you'll just, yeah. So what we're going to do is we're going to take our lead from here. We have a term back here. We have a term that goes with the squared, and a term that goes with the linear. Sort of what we're going to do. That's probably more right this way, right? Doesn't really matter what you call them. Okay. So you may have seen it with the A0 plus A1x all together on the top. I find that unhelpful because you're going to integrate these two things in separately. So I'd like to keep them separate. The first one will integrate using arctan, and the second one will integrate using an ordinary substitution. There you go. And if you have, this will probably never come up in the exam unless they ask what format is it going to be in. But if you had something like this, right, with a power on it, you'll have one set for each power. So you'll have and then these bits over here belong to the other parts of the partial fraction. So what happens is that the linear terms produce one, each power produces that many terms in the result, but the quadratic terms produce twice as many. So back here, can we fit it all on one screen? So this single linear term produced 1, this double linear term produced 2, this triple linear term produced 3, but here the single quadratic term produced 2, the double quadratic term would produce 4, the triple quadratic term would produce 6. It's always twice as many. There you go. Now we need an example of doing this, okay? But these are the things that are most likely to come up. If your quadratic term is irreducible but doesn't look like that, you need to complete the square. Because you're going to have to do that eventually anyway. All right. So here we go. Here we go. Not that you would ever really want to integrate something like this, but just for completeness' sake. All right. So let's just do something. You should just check if it's been factorized properly. If this had been an x minus 5, I could have separated into an x plus root 5 and an x minus root 5, which would be linear terms. So this one step at a time. This bit here is an irreducible quadratic. It doesn't factorize any further, so I can do this. It will be oh, damn it, my naming system's gone crazy. I'm just going to use all different letters for all of them and see how far I go. This went into this with an extra x. but I'm also going to have to do it for the single term. Okay, so I've done it for the quadratic, and I've got an a and a bx. I've done it for the single power, and I've got a c and a dx. So the next one is a linear, and I'll do all three of its powers. The next one is linear, and it's only there once. The next one is quadratic, and it's only there once. What are we up to? I. And now I've gotten to the end. This would take a lot of effort to figure out what the actual coefficients were, but that's not the point of the exercise here at the moment. The point of the exercise here at the moment is to show you what the format will be. It is not uncommon for people to just say, what's the format? Okay. So, the next part of the problem, so conceivably I could put this all over a common denominator. This one I would have to times by x minus 1 cubed, x plus 5, x squared plus 5. This one I would have to times by x minus 1 cubed, x plus 5, x squared plus 5. This one I would have to times by an x squared plus 4, because we've only got one of them, and an x minus 1 cubed, and an x plus 5, and an x squared plus 5. And so on. And you'll notice that one of the problems that's going to happen is that with the quadratic ones, you can't make them vanish by subbing stuff into them, because they don't have zeros. You could sub complex numbers in if you wanted, but it would cause pain elsewhere. Okay. So, let me do one from beginning to end, including the integration itself. Well, actually, no. Yeah. All right, maybe not. That's partial fractions. The procedure is the same. The format is the bit that's new to you. In a completely technical sense, you've seen multiplying fractions by common denominators before. So that is hopefully, according to the people who are teaching you, something that you can do. But that means that you need to remind yourself how to do that. The next part is integrating it. Okay. And so I'm going to get up to the point where I've already done my partial fractions. There we go. This is the partial fraction I ended up with. You can abstract from that what the actual original thing was, if you like, but we know what's on its denominator. It was an x plus 4, an x minus 1 squared, and an x. That's where this came from. So integrating this means that we have to know how to integrate each of those pieces. These three, you know how to integrate. I'm just going to do each of them one at a time. Starting at the end. The 15 is technically a constant multiplied on, and it's really 15 times 1 over x, and so it's 15 ln x. And it needs to be an absolute value, that's important. The next one, which is this one here, the 2 is a constant multiplied on, and we'll get ln of... But because this isn't just x, we'll divide by the derivative, which is 1 anyway, so it all works out nicely. This one I can't use logs because ln is designed for when this is a const, then this is just x minus 1. So I'm going to have to rewrite it in a way that I can use, which is that. So the 5 will still be there, and the power will go up by 1, up to minus 1, and I'll have to divide by the new power. Like that. So that's these ones. So anything where it's not a single power, you need to rewrite it as a negative power and do it that way. Technically, I should have mentioned that since the inside isn't 1, I have to divide by it, and its derivative is a constant, I have to divide by that constant derivative, but the constant derivative is 1 anyway, so I don't have to worry about it. The next stage is these two. All right, so let's see, I could rewrite it, but we've already just done rewriting it to do the partial fractions, so it's probably not worthwhile. Next thing on the list is substitution. Well, the top is nearly the derivative of the bottom. It's got the right number of x's in it at least. And so if I do a substitution, then du on dx will be 2x and then times by the dx to get that. And that's pretty close. I just need a 13 instead of a 2. So I'll divide both sides by 2 and times them by 13. And so that's now going to allow me to do my integral. It's now 13 over 2 du over u. Beautiful. So the 13 over 2 is a constant. I'll get ln of u. And u was x squared plus 4. Like that. And last, but not least, and actually it's the best/worst one, is this one. So let's see. Could I just do it? Possibly, if I knew my integrals correctly. If not, maybe I could rewrite it to look more like something. And gosh golly, if that was a 1, it would be an arctan. So if I divide the top and bottom by 4, I'll get that, which is the same as this. So the 3/4 can move off like that. And this would be x on 2 squared plus 1. So the 3/4 will stay there because it's multiplied on. This would be arctan if that was just an x. It's not an x, it's an x on 2, whose derivative is a constant, so I can divide by that constant, which means timesing by 2 over 1. So I don't need to use trig substitution or anything, because I can use my knowledge about arctan. And so therefore, the original integral is all of these pieces added together. Minus 5 x take 1 plus 13 over 2 ln x squared plus 4 plus 3 over 2 arctan x on 2 c. That's how you do one of these integrals. If you had to do a full partial fractions and you didn't feel you had time to figure out what the things on the tops of the fractions were, like your ABs, capital A, Bs and Cs, You could always say this is the format, and when I integrate that format, this is what it would look like, and just leave the A's and B's and C's out the front. So instead of a 5 here, it would have just been like a C or something. And that at least gives you the right shape and shows that you know how to integrate stuff. It's just skipped one part of the working. Right. There are a couple of other nuances that may happen, and one of them is what happens when your piece on the bottom doesn't look like an x squared plus something. And that takes a little more creative work to deal with. There are multiple ways of dealing with that. But the best way, for the purposes of what we're doing here, is probably to complete the square so it looks more like something squared plus something. So if I saw something like this, maybe not a 3. Something like that. Maybe with another bit. Okay. I would know that my partial fractions would tell me that I could integrate, I could separate it like this. Like that. So one of the rules I told you earlier, this one back here, that one applies just as well to any quadratic on the bottom that doesn't factorise. But how would you know it didn't factorise without attempting to? Yeah?
What about if power of x is greater than 2?
How would you integrate that?
How would you deal with the partial fractions?
You wouldn't. So you're saying, what if you saw something like... Oh, can I go back to that in just a second? So you could split it up like this, and that'd be great. It would require you to do this with substitution. Problem is that you can't... When you try to do this with substitution, you're going to get a 2x plus 6, which doesn't exist in your function, which causes a little bit of a problem. So you've got choices. You can just do it, and what will happen is you'll end up adjusting it and getting another bit that looks like this. Alternatively, you can be very creative, and since you're planning to do substitution anyway, do that. And just put the derivative of the bottom there instead of x. And it'll work. Yes. Problem is, of course, this one over here will have to be completed the square to do anyway. So we'll have to complete the square here, which I've shown in other seminars that I did actually today, that you'll have to complete the square. You'll get an x plus 3 all squared and a 1. And you go, oh, wow, look at that. That's arctan, except it's got an x plus 3 in it instead of an x. So actually back here, I could have, if I wanted to, being very creative, instead of doing this an A0x, I could have done it as an A1x, I could have done it as an A1 times 2x. And it would have made my algebra very nice. I wouldn't have had to divide by 2 anywhere. Okay. You asked what would happen if it was something like that. All right. Now here's the really nice thing. We don't need to know anything about cubics because the fundamental theorem of arithmetic yes, says that you can factorize anything into linears and quadratics. So what I need to do is figure out how to factorize this. Now I know how to factorize that already because that's something that I happen to know. But I do know that -1 goes into that to produce 0. I know that -1 cubed plus 1 equals 0, so x minus 1 must be a factor. So I can use division to figure out what the other one is. Not if it's an x cubed, no. Are you ready? Nice leaves. X cubed divided by x is x squared. X squared times that is x cubed minus x squared. And when you subtract that, you get x squared. X squared divided by x is x. And x times that is x squared minus x. And when I subtract that, I get x. And x divided by x is 1. And 1 times this is x take 1. And when I subtract that, I get 1 minus minus 1, which is 0. Excellent. It should come out as 0 because it goes in. So therefore, x cubed plus 1 is x minus 1 times x squared plus x plus 1. Lovely. And so my format is, and this doesn't factorize. Yep. That's a plus 1. Yep. No. Nope. It only works with complex numbers. So when you put, if a real polynomial has a complex root like I, for example, then minus I will have to be a root as well. But that only works if it's like if it had 2 plus I, then 2 minus I would be 1, but you only switch the sign on the imaginary bit, and minus 1 doesn't have an imaginary bit. It's a real number. Yep.
I think you're crazy too. -1 is the 0, so x minus -1 is 0.
Oh, sorry, is that what you mean?
Yeah, that's what I've been talking about this so long.
Sorry about that.
Also, when you go down,
That becomes a 2, doesn't it?
then your long division becomes a 2.
Yes, okay. Sorry about that. Let's just scratch that. It's okay. I've told you multiple times today that I lose minus signs, or add them. Yep.
So what happened when you did your partial fraction and you ended up with a quadratic term, perhaps cubed, because it appears multiple times?
What would you do when you integrate it?
Yeah.
I'm just going to write that down there so that it's done. That's the correct answer. Sorry about that. And this doesn't factorize. And so you're going to end up with like that. Okay. What would happen when you tried to integrate it, when you had one of these ones? Is that what you're asking? Like something like that? How would you integrate that? You would use a reduction formula to turn it into x squared plus 4 to the 1, which you could then do with arctan. Only that you won't, because they won't ask you that. But that's how you do it. There's a reduction formula that reduces the power there down to lower powers. Yeah. It's a fabulous reduction formula. You actually, when you do the reduction formula thing, you prove it backwards. And you actually, when you try and do the reduction formula, it makes the power go up. But that's okay, because you just sort of flip it around the other way and the power's going down. So it's a fabulous magic trick. But you'll never see it in a Maths 1A exam. Yeah. So the problem with partial fractions that I see is that what, you get like a lecture on it? And it's really like detailed stuff. So they put it in so that when you need it for future purposes, you can go, oh, that was partial fractions, and you can look it up. But then they still examine it, and the way they get around that is they examine it on the something that's quite basic, and you're likely to see something that only has a couple of bits in it. So it'll be more like something like this one. It may have a quadratic one in it as well. Or they'll just give you straight one of these without having to do the partial fractions bit. So in past exams, you've usually had one that's got linear factors on the bottom, and then one of these straight without having to do the partial fractions. So that's the way they get around assessing something that they only did a lecture on that's really quite complex. Right. Well, that'll do for partial fractions, I think.